Right, hello, it's Science, Mr. Roberts time. Mr. Roberts. Do again. Hello, it's Science, Mr. Robertson time, and you have another video right here, right now, and it's going to be a little bit different, this one. I want to show you how to draw force diagrams. In the class, we're going to do lots and lots and lots of them. Try and take it in, try and see what I'm doing, and then hopefully you can understand and do some in class yourself. A force diagram shows me all the forces on an object. Starting with the most boring example, I have a block standing on a table, floor, whatever. On planet Earth, we know that that block is going to be pulled down. There's going to be a force of gravity going down. So there's a big arrow for gravity going down. But the block's not moving. It's staying there. So the force down must be equal to a force going up. There is, we say, an equal and opposite reaction. It's opposite, so this is going down, so it must be going up, and it's equal, so it should be the same size of reaction. It's the reaction of the object. It's why the pen in my hand is not falling through it. Gravity is pulling the pen down, reaction of my hand is keeping up. Balanced, it's not moving unless I shake. So it's perfectly still. It is in balance. Okay. Simple. And this is my diagram, my picture here. Den här diagram med svenska. Force diagram is a picture like this. Let's do something else. I got a block here, and I'm going to get one person to try and push that block. But it's really heavy. And one person can't move it. But he tries. Trying to move it. So I can put a push force. There is a push force going that way. It's being pushed in this direction. Is it moving? No, it's not moving. And that's because of that rubbing force, friction. It's so heavy, it's rubbing on the ground. It's not letting it move. I have an equal and opposite force of friction. It stops it from moving. But what happens to my picture if I put in another person to push? That means my push is going to get bigger. Maybe it might be so big that the friction may be a little more friction. But maybe two people together can start to push and can start to make it move. Now, what we have in this picture is an unbalanced force. This object here, this block, is going to accelerate. Get faster and faster and faster, which is great. So you start slowly and then you faster, 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 faster. But that can't happen forever. Oh no. Oh no. And if I go faster and faster and faster, I'm going to do more and more rubbing on the ground. That means more and more friction. So if it goes faster, so I've got to do going faster, then that means to push. I can't push anymore. I'm pushing it. But the friction is going to get bigger. The friction and the push equal each other. The gravity and the reaction equal each other. What I have now is a balanced force. I have no accelerating. So what I have is I have my maximum speed. I'm pushing as hard as I can. The friction is stopping me on the bottom. It's the max limit. And again, I can use a picture like this to show all of the different forces that we have. Friction is a very important one, because friction is the force that slows things down when they rub together. In class, what we're going to do is give you lots of different examples of drawing these kind of pictures. You'll need to think in your picture, is there any gravity? Is there a reaction? You'll need to think, is there any air resistance? We'll come to that this week too. As well as gravity. Well, gravity, I've got gravity. My gravity, my gravity. There could be a push force. There could be a thrust that comes from an engine. There could be so many different forces. In these pictures here, the most important thing is you look for the size of the arrow and the direction of the arrow. Those two things are what I'm looking for. Is it the right size? How big the arrow is? Is it in the right direction? Hope this helps. We'll do some more of it in class. Take care.